The lecture is structured into an introduction, early diagenetic processes in sediments. Then I will focus a bit on methods and instrumentation for measurements of sediment water fluxes, because this is really my field, in situ technology, and the advantages but also the pitfalls of measuring fluxes in the sea. Then I give a couple of examples of benthic flux estimates. Continue with the introduction of sedimentary archives, that might be interesting for you. And then if there is time, I will give you some of my thoughts or wishes regarding benthic-pelagic coupling in models from the view from a non-modeler. And then further reading, that's for you, for later. This lecture is focused on coastal seas mainly, and not so much on the Baltic Sea in particular, because I didn't work really yet in the Baltic Sea, and I don't dare to present other people's results. But it's more general about coastal seas. The special thing about coastal seas is that the water column is quite shallow, and there is not much time and space for material that is transported from the land to the sea to be processed in the water column. So most of things that come from the land, from industry, from agriculture, from Christoph's pigs, and also from shipping, ends up in the sediment. Also there is deposition of remnants, things that people don't use anymore. The seafloor is also affected by by demersal fishing. Then we have the deepening of shipways, but maybe in the Baltic Sea also the pumping up of the phosphorus-containing sediments, as we heard yesterday. And then as an emerging activity in coastal seas is the development of offshore wind parks, and this involves intruding large pylons into the seafloor. The pylons have to be secured, and a large part of the seafloor around the pylons will be covered, for example, with geotextiles. And these geotextiles also affect the interaction of the seafloor and the overlaying water column. And these are all reasons why I think that the sediments, especially in shallow areas, are important, and it's important not to look but also to benthic and pelagic coupling. Continental shelf. These are sediments in water depths less than 65 meters approximately, are worldwide covered mainly 47% by sands. So the majority, or almost the majority, or half of the sediments consist of permeable sediments, sands. 37% are muds. Only 6% is covered by gravel and rocks. 6% consists of coral, and 4% of shell debris. I give you two examples of two different sedimentary systems. The left-hand side is the German Bight within the North Sea, and all this whitish area with the red dots, these sediments consists mainly of fine to coarse sands. The yellowish greenish part is sandy sediments with a few percent of mud, and only this one, the blue part, represents muddy sediments. So the majority of North Sea sediments are permeable sands. In contrast, the Western Black Sea shelf is a really shallow shelf. The deepest part of the shelf is about 70-80 meters, and only a small part in front of the Danube River mouth consists of coarse sands and mud, and then already a long stripe of muddy sediments and river-originated sediment with fine particle sediment are stretched to the south. A large part of the shelf is the so-called starved sediment. That means not much particulate material is accumulating on the sediment, And these sediments consist mainly of shell debris. So to slowly warm up, I will show you a few examples of different sediment types and how it looks like. This is an example from the Dogger Bank. This is a quite shallow area here in the North Sea, only about 30 meters deep, and we were there this year in June. And you see a sandy sediment covered with a few shells and benthic fauna that is running away from the video sled. In contrast, we have small areas, as I said, in the North Sea that contain more muddy sediments, but the mud is here also mixed with sand. And you see here holes of arenicola. And you can also observe that in this area, this is deeper, it's about 40 meters deep, lots of particulate material is settling to the sea floor. Here the currents are slower and fine-grained material is able to settle to the sea floor. This is an example from the Black Sea, and this shows that the sediments do not exclusively consist of lithogenic material, but large part of sediments are covered by marine fauna. Here in this example, lots of filter feeders and a few anemone and spongy. This is in about 22 meters depth. In greater depths, in about 46 meter depths, this is an example from the so-called sediment-starved shelf, and we see here lots of empty shells and a few small living Mytilus shells, a few macroalgae, Philophora, and opportunistic filter feeders, ascidians. These large Mytilus shells that are on the surface are about 1,500 years old. And this is an example how a healthy benthic ecosystem with epifauna, filter feeders looks like, and this is the contrasting example how a degraded benthic ecosystem might look like due to eutrophication and lots of settled material, and after hypoxia most of the shells, the mussels are dead. And these two pictures come from this area here on the northwestern on the northwestern Black Sea shelf. All these images were taken with a video sled. It looks like a real sled, and it's towed behind the ship at lowest possible speed, mostly 0.5 knots. And it's equipped with a camera and laser pointers and lights. Okay, as I already pointed out, the benthic and the pelagic compartments are in close contact and in a two-way interaction. It's not just benthic-pelagic, but practically it's pelagic-benthic-pelagic interactions. So the material that settles to the water column, to the seafloor, is decomposed in the sediments, and the part that is not buried is released again to the water column and can then fuel productivity processes, biological processes in the water column. So both systems influence each other. And these influences can be direct or indirect, and they can operate on tidal or interannual time scales. So there's import of material from the land and also from offshore areas. We have primary production of biomass, regeneration in the water column, and usually below the pycnocline we have then sedimentation, regeneration. Part of the settling material is permanently buried in the sediment. We have also, not to neglect, benthic primary production, regeneration of nutrients. And the benthic system, the sediment, is habitat for organisms in fauna, epifauna, flora, demersal fishes, and it receives also the legacy of anthropogenic perturbations, pollution. Estimates show that about globally 500 teramole of carbon is the global productivity on the shelves. About 300 teramole of carbon per year are respired on the shelf. And 150 teramole of carbon is respired in shelf sediments. That means that the sediments account for 50% of the shelf respiration. That's quite a large amount. Other estimates show that the proportion of benthic to total respiration on shelf depends primarily on the water depth. So the benthic contribution varies from about 40% in shallow water depths to only a few percent at about 100 meters depth. So the water depth plays an important role. As I said, in shallow seas, the sediment is the most important site for the accumulation, storage, and also biogeochemical transformation of organic matter. So in the upper water column, nutrients are taken up by phytoplankton, and they oxygenate the water column. Phytoplankton is grazed by zooplankton, and the fecal pellets that fall out at deeper depths, the organic particles, are then in the water column are beginning to be degraded by bacteria, and then it goes in the other way. So nutrients are again released from organic particles, and it takes oxygen to decompose organic matter. And a large part is then degraded within the sediments. So we can say that the shelf sediments are the memory of the pelagic system. So on the long term, what happens in the pelagic system is mirrored or is accumulated then in the benthic system. So, for example, if you, as you all know, also in the Baltic Sea, the input of external nutrient sources has been reduced for several years now or decades now, but still the sediments contain a large amount of nutrients from past eutrophication. And this is what I mean with shelf sediments are the memory of the pelagic system. Hydrodynamic conditions and transport mechanisms into and out of the sediments, they determine the linkage of sedimentary processes to the overlying water. We have in the water column gravitational settling of particles and aggregation of particles, adsorption, desorption of contaminants, and then the surface currents come into play. Then once the particles reach the sediment, there is, due to bottom currents, resuspension, lateral flow, and we have also transport between the sediment and the water column due to bioturbation and bioirrigation and advection and diffusion. So to summarize, the most important benthic transport processes are gravitational settling, bioturbation, bioirrigation, the so-called bioirrigation, molecular diffusion, pore water advection, and burial due to lateral sediment transport.
What is the difference between bioturbation and bioirrigation?
I will show in a few slides. And these transport processes are strongly affected by boundary layer flows, which cause water currents, surface gravity, waves, and turbulence. And these processes control the benthic and pelagic coupling. This is how, in a biogeochemist's perfect world, would look pore water gradients in the sediment. With pore water gradients, the pore profiles, I mean the concentration profiles of solutes within the sediment. oxygen penetrates only for a few millimeters into the sediment and is quickly taken up due to decomposition of organic matter. So oxygen slowly approaches zero. The nitrate concentration increases due to decomposition in the oxic part of the sediment, and then in the more reducing part slowly is decreasing because the oxygen is then used for decomposition of organic material. And then in deeper water we see an increase of ammonia instead. So this is like in a perfect geochemist's world. And this is how perfect pore water gradients might look like. We might observe linear gradients in a pore water, and a linear gradient can be interpreted like a solute concentration in the pore water is controlled by diffusion from a source at B to A, and there is no advection and reaction between A and B taking place. On the right hand side, this convex gradient can be interpreted as a removal or a downward flux of a solute from A to B. We can have concave gradients, and these concave gradients are formed due to production or the upward advection of a solute in the pore water from B to A. And a curved gradient occurs if the concentrations on top and in the deeper sediments are equal, and somewhere in between production or consumption creates a maximum or a minimum. So, but we are not in a perfect biogeochemist world. This shows life in the Wadden Sea, lots of epi and infauna. So what do you think is happening to these ideal pore water profiles if these guys are active in the sediment?
There's more oxygen penetrating deeper in the sediment.
So, say it again?
The oxygen is going down, more down
Yeah.
the sediment.
Yeah?
So it's not all those processes
Yes.
are going, so the oxidation might penetrate deeper.
Yeah.
So the reduction also will be shifted.
Yes, exactly. That is what takes place. And now this is the impact of bioturbation, bioirrigation. Bioturbation is the mixing of sediment particles due to the activity of the organisms when they move or crawl in the sediment. And bioirrigation is the exchange of bottom water and pore water due to the boring activities of organisms. So here, theoretically, no particles are transported, but the pore overlaying water is flowing into the burrows and then ventilating the nearby sediment. Does it answer your question?
Yes. Also, I knew from you that
This photograph shows impressively how the ventilation, the effect of the ventilation. So this shows the transport process inside the burrow caused by bioirrigating macrobenthos. So here you see the burrow, and around it the sediment is oxidized. And further away from the burrows there is anoxic or reduced sediment. So this represents the burrow, and the water from the water column flows here into the burrow. And we have passive flow inside the burrow. We have diffusive pore water transport across the walls of the burrow, but we have also advective pore water flow if the burrows are in permeable sediments. And the consequence of bioirrigation, as this picture shows, oxic part of the sediment next to the burrow, reducing sediment further away, and it affects, as you correctly pointed out, the diagenetic processes in the remineralization. For example, in oxic sediment and oxic pore water, iron occurs as iron hydroxide bound. But under reducing conditions, the iron is reduced to iron 2 and in solution. So if oxidized water penetrates the sediment, then this dissolved iron is again oxidized, and then we have this iron hydroxides again. And in the pore water, in the pore water, due to the ventilation and the oxygen penetration, the dissolved phosphorus concentration decreases. The dissolved iron 2 decreases, and also ammonia in the water, since this is a reduced compound, decreases. And in the sediment matrix, total phosphorus, so particulate phosphorus, increases since phosphorus adsorbed onto iron and aluminum oxyhydroxides, and manganese increases in the sediments. So the consequences of bioturbation. If you, for example, would inject a tracer into the sediment, and this solid line may display the shape of the tracer injected to the sediment. And if you have bioturbating organisms in the sediment, and if you wait for a few days, then due to this reworking of the sediment, these markers are somehow, these peaks somehow disappear. And after about, this was 25 days, for example, and if you wait even longer, so the signature of the tracer is completely mixed and distributed over the sediment. And this is one of the problems that we face if we try to date coastal sediments with lead-210 and cesium, because due to the reworking of bioturbating organisms, the peaks that we are looking for are disappeared over and are distributed over the larger area of the sediment.
Can I ask why is
Yeah.
it 0 at the surface? Concentration. Should we start with?
It's an example, and somehow, I guess this example is maybe taken from sediment that should be dated with cesium, because cesium 137 is a fallout radionuclide due to nuclear tests and the Chernobyl accident. And Chernobyl was in 86, and the end of nuclear tests was in 63. So that might be the reason why that this example is taken from there, and the concentration is 0 at the surface. But otherwise, normally, if you inject something, then it should be a peak on the surface. Gravitational settling and the currents in the coastal sea determine to a large extent which type of sediment we observe. In areas with stronger currents, only coarse-grained material is able to settle to the seafloor, and the fine-grained material stays in the water column. And in areas with low currents, then also the fine-grained material can settle. As I showed before, in the North Sea, there we find mostly coarse to fine-grained sediment. The North Sea German Bight is characterized by a strong tidal forcing, so the water column is constantly in motion, and only coarse-grained particles are able to settle to the seafloor. And this is reflected also in the permeability of sediments. If we measure the permeability of surface sediments in the German Bight, we can see here this is a low permeability, this is high permeability. That here in these muddy areas, permeability in the sediments is low, and towards the sandy areas, the permeability of sediments is higher. So sediments can be divided into permeable sediments and impermeable sediments. And the sediment permeability, the dividing line is chosen at 10 exponential minus 12. Sediments that have here a higher permeability. Here the transport processes inside the sediment are dominated by advection, and at lower permeability the transport processes are dominated by diffusion or by bioturbation. So the boundary flow conditions and the sediment permeability determine whether advection or diffusion dominates the transport processes in sediments. And the meso and macrofauna, of course, as you observed correctly, can enhance the transport of solutes and particles by bioturbation and bioirrigation. And in coastal permeable sediments, biological transport can be as efficient as advective exchange. So this picture shows a sediment that is stained, and here there is a wave motion exposed. And to illustrate advective pore water exchange due to boundary currents, we can see that here at the ripple crest, the stained pore water is released from the sediment. In the ripple troughs, unstained water from outside is penetrating the sediment. So if we plot this in a graph, we can see that under advective conditions, so when there's a strong wave motion, then the tracer is released quickly and in a higher concentration from the sediment than under stagnant, so there's no motion, under diffusive conditions from the sediment. This to a large extent influences the fluxes from the sediments. So an advective release of solutes is higher than diffusive release. So why does this matter? The currents due to tidal forcing and wave motion, they create pressure gradients, and these pressure gradients may enhance the sediment fluxes over permeable sediments. Irma told us in her presentation that she did sediment core incubations. So what do you think what happens if you put a sediment enclosure onto a sediment exposed to wave motions? What happens here inside? Yeah, sort of nothing. Yeah, sort of nothing, because all the wave motion, the currents are blocked, and we create stagnant conditions. So if you have here stagnant conditions, the fluxes that we try to measure in our enclosure are different from them outside, because they are lower than here. And this is why all this, the observation of these processes of advective and diffusive transport processes really matter. So the flow regime really changes due to stagnant conditions. There's a shift from advective to diffusive transport, and the release of solutes from the sediment changes. So when you're measuring benthic fluxes, either in situ or ex situ, a proper simulation of the flow regime is crucial for realistic results. Otherwise, you can produce any number you wish. So this is a nice sketch of settling material and particle reworking. So the flux of solutes from the sediment determine the degradation processes inside the sediment, but also the released substances determine or influence the primary production in the overlying water column. And the degradation processes in the sediment depend on the flux of electron acceptors like nitrate, sulfate and oxygen into the sediment. And then we have a very interesting layer next to the sediment. This is the so-called benthic boundary layer. And this layer is characterized by friction and this friction is created between a steady sediment and the water column above that is moving. And here in this small layer, it can be from a few micrometers to a few centimeters. There are really large gradients of bottom shear stress occur, and this largely influences the exchange of solutes between the sediment and the overlying water column. Now let's have a look at the redox regimes in sediments. If we consider the open ocean, the water column is quite deep, and also the deposition of organic matter due to lower productivity is lower than in the coastal ocean, and the oxygen penetration into the sediment is deeper than in the coastal ocean. In the coastal ocean, we have a fairly thin layer of oxic conditions in the sediment, then a layer of hypoxic conditions. The largest area in the sediment is characterized by anoxic conditions. The special case, for example, of the deep basins in the Baltic Sea and also in the Black Sea, the oxic-anoxic interface is shifted in the water column, and this we call oxenic conditions if the water column above the sediment already contains hydrogen sulfide. And sometimes we call this a liquid sediment, because in this anoxic sediment, in this stagnant water body, lots of substances are accumulated. This sketch should illustrate pore water profiles in the oxic part of the sediment and in the anoxic part of the sediment. I will now, in the following, demonstrate the major transformation pathways of organic matter in the sediment. So under oxic conditions, there is aerobic respiration and nitrification. In the suboxic part of the sediment, nitrate reduction, so the oxygen in the nitrate is used to oxidize organic material. We have denitrification, manganese reduction, iron reduction, and sulfide oxidation. In the anoxic part of the sediment, we find anamox. This is the anaerobe ammonium oxidation, sulfide reduction, and methanogenesis. In aerobic respiration, organic matter is decomposed by the use of oxygen, is oxidized and released from the organic matter. It releases CO2, nitrate, phosphate, and a large part of water. From the suboxic or the suboxic sediment, ammonia may diffuse to the oxic part of the sediment, which is there oxidized by bacteria like Nitrosomonas and Nitrobacter. All these microbial reactions are dependent on temperature and also on substrate. So the higher the temperature, the faster these microbial transformation processes take place. So we can imagine that during climate change or global warming, and with warming of the oceans, also the bottom temperature increases, and these microbial processes proceed much faster. In the suboxic sediment, part of the organic matter can be oxidized by the use of oxygen, as I said, from nitrate. There's a process that recently gains more importance, which is a dissimilatory nitrate reduction to ammonia, and denitrification, and these processes are competing for substrate. For manganese reduction, iron reduction, organic matter is decomposed by the use of the oxygen in the iron hydroxide and manganese oxide. And as the products from the decomposition are always CO2 or bicarbonate and the reduced compounds of manganese or iron or nitrogen, phosphate and water. In the anoxic sediment, the oxygen from sulfate is used to decompose organic material, and this is realized by archaea and bacteria like Disulfovibrio. For methanogenesis, archaea use organic matter to decompose it to CO2 and to methane. So let's have a closer look onto the nitrogen cycle. So depending on the redox conditions in either the water column or the sediment, we have either nitrification or as long as we have nitrate in the water column, denitrification, and or dissimilatory reduction of nitrate to ammonia. Denitrification is often seen as an ecosystem service, since during denitrification nitrogen gas is produced. And nitrogen gas escapes from the ecosystem. In the anoxic part of the sediment, we have another process that produces nitrogen gas, and this is anamox, it's the anaerobic ammonium oxidation. So the oxygen from the nitrite, an intermediate product, is used to oxidize ammonia, and then nitrogen gas is released from the sediment. But then there is a competing process, which is the dissimilatory nitrate reduction to ammonia. And here, organic matter is decomposed or oxidized by the use of the oxygen from the nitrate. But here the result is ammonia. And this process conserves nitrogen within the system. And it has been recently observed that this DNRA is a major nitrogen reduction pathway in coastal ecosystems. And DNRA is favored over denitrification, so it outcompetes denitrification at increased carbon loads in the system, so at high carbon to nitrate ratios, and at increased sulfate reduction rates, and at increased temperatures. So if we face global warming, DNRA might outcompete denitrification, and this so-called ecosystem service will be less important, and the nitrogen will stay in the system and is not removed to the atmosphere. So eutrophication and climate warming will support the DNRA. And this is of critical importance also for the modeling, for predicting of eutrophication trajectories. Now we switch to the operational part. I will now introduce methods and instrumentation for the measurement of sediment water fluxes. We can measure these fluxes by two ways: ex situ and by in situ methods. You have experience with the ex situ methods. And there you take sediment cores and incubate them either on the ship or in the lab. So you take, for For the ex situ measurements, you take sediment cores or slurries. You can do light and dark incubations for measurements of benthic primary productivity and respiration, nutrient fluxes, isotope tracer experiments to characterize the nitrogen cycle. You can measure micro profiles of oxygen penetration in these cores, and you can take pore water using rhizomes. What I forgot to mention when I talked about the nitrogen cycle is to measure DNRA and denitrification. It is necessary to do tracer incubations. So usually you do it ex situ. You add N15, so nitrate enriched in N15 to a sediment core, to a slurry, and then you incubate it for a certain amount of time, and then you can measure the amount of N15 which is enriched in the nitrogen gas that is produced to the denitrification, or the N15 enriched in the ammonia. And then you can see the partitioning between denitrification and DNRA in the sediment. In situ methods can be divided into non-invasive methods. That is, for example, eddy correlation to measure benthic oxygen uptake. Then you can use a laser scanner to measure the microtopography and the changes of the microtopography of the sediment. You can use high-resolution cameras for bed form migration and fauna analysis, and all kinds of current measurements, bottom currents. Invasive methods include benthic chamber landers for nutrient fluxes and oxygen uptake, but you can also do these microsensor oxygen or nitrate profile measurements in situ on a lander. Now I will present these methods in a bit more detail. A very common method is Van Veen grab. You simply take a surface sediment sample from the seafloor, and with this kind of grab you can do faunal analysis, grain size analysis, permeability measurements, volumetric oxygen consumption, or slurry incubations of measurements. Or you can use a box corer to take large sediment samples of about 50 centimeters depth, and then you can subsample this box core for sediment cores. You can also do permeability measurements, fauna analysis, and grain size analysis. This large and heavy box corer is particularly useful if you want to sample compacted sediment like sands or shelly sediments, because it's heavy and it can penetrate this solid upper sediment layer. Another instrument is the multicorer, and with the multicorer you can simultaneously sample a number of cores. So this corer is equipped with plexiglass liners which are lowered to the seafloor, and then the sediment cores are taken, and I will demonstrate this in a small video. So the corer is equipped with the plexiglass liners, and on a wire from the ship it's deployed overboard. And the cores are flushed with water all the way through the water column. And then the corer reaches the sea floor, and it has to sit for a while until the tubes penetrate the sediment. And then when you lift the corer, the lids below are closed and the cores are taken up. And then pay attention to this corer as it goes up. You see? We had a sand eel in the core, and the whole core was disturbed because the sand eel suddenly realized, oh, I'm in the core. So I will stop here for a moment, and we have a short break until 9:30. Shall we continue? Okay, second part. This slide shows the incubation of sediment cores, and we have in our institute a benthic lander which is called Sandy, and this is our lab incubator, Andy. So he's really brilliant and spends all nights in the cool lab on the ship. So this is the incubation of sediment cores for benthic respiration. You can see that they are covered with foil to keep them dark. And this is a similar setup, but for benthic primary production. So the cores are illuminated with a defined light field. And we have also stirrer discs in the core to simulate the near flow bottom currents and to avoid the buildup of a thick benthic boundary layer that may block the fluxes. These two graphs are examples of the oxygen concentrate, the evolution of the oxygen concentration in the sediment core over time of incubation. That might look familiar to you. And the other graph shows the development of the concentration here of nitrate over time in the 4 incubated sediment cores. And we can use these graphs to calculate the benthic fluxes. And the flux is calculated from the height of the water column in the core and the changes of the concentration in the water column in the core over time in the enclosure. And this gives us then the flux at the sediment-water interface, for example in millimole per square meter and day. This is a quite robust way to measure benthic fluxes, and is also a good backup on the sea if the weather is bad. Usually one can always take sediment cores and then we incubate them in the sediment. But landers we can deploy only in quite calm sea conditions. This shows how we measure the oxygen penetration into the sediment. We use a micromanipulator and a small needle-tight optote, and the optote is driven in tiny steps into the sediment, and we measure the oxygen concentration in the sediment overlaying water and in the sediment. And this scale is micrometer, and you can see that the oxygen rapidly decreases in the upper micrometers into the sediment. This is an example from the German Bight from a sandy sediment. These plots show how different these oxygen profiles might look like. This is an example of the oxygen penetration in oxic bottom waters. And here in hypoxic bottom or oxic to hypoxic bottom waters, you see that the penetration depth is even shallower into the sediment. And this is in the hypoxic to anoxic bottom water. We have small amounts of oxygen concentration in the water column, and oxygen is taken up already at the sediment surface and doesn't penetrate into the sediment anymore. We can calculate the oxygen uptake by applying Fick's first law, and we can calculate these diffusive benthic fluxes across the sediment-water interface because they are proportional to the concentration gradient and the diffusion gradient. We can plot a linear regression to the gradient, and the flux is calculated from the changes of the concentration with with depth. And we also used the diffusivity of a certain substance, the diffusion coefficient of a substance in the sediment, and the sediment porosity. And the effective diffusion coefficient in the sediment is calculated from the diffusion of a substance in seawater, and porosity, and a certain sediment resistivity factor. And there is a relationship between the porosity and this sediment resistivity factor. We also sample the pore water from the sediment, and there are various methods. You can slice the sediment in slices and put them in a pore water press. And usually this is a tedious procedure because you need to do it in a glove bag in a nitrogen atmosphere to avoid oxygen pollution. Yeah, you're nodding. You know that. And then then you can also use peepers. That is like a jelly-filled sword which is implanted into sediment. But in recent times, more and more people use rhizomes to extract pore water from the sediment. And the rhizomes consist of a hydrophilic porous polymer and connected to a tube. And you can use a sediment core that is equipped with holes, and when we take the core, we close the holes simply with tape. Then we take the core from the corer, remove the outer tape, then we inject the rhizomes, and then we pull up syringes. You can either do it by hand very quickly, ideally in parallel, or you can equip it with the peristaltic pump and fill the syringes with the peristaltic pump. And in this way you get the pore water from the sediment, also the gaseous phase, without contamination with oxygen. And this is an example how these pore water profiles taken with rhizomes might look like. The upper row shows an example from an area in the German Bight near the island of Helgoland, from a muddy area and from an area with coarse sands. And please pay attention, in this muddy area the concentration is much higher in the pore water, here for in this case for ammonia, than in sandy sediments. This plot shows the profiles of phosphate and silica, and for both silica and phosphate the concentration is much higher in muddy sediment than in sandy sediments. And when we look at the pH profile, pH is also an indication for the intensity of the decomposition of organic matter, because during the decomposition CO2 and bicarbonate is released, which causes a decrease of the pH during decomposition of organic matter. So the gradient here across the sediment or water interface is larger in the muddy sediment, so there's more decomposition than here in the sandy sediment. Now we switch to in situ methods of measuring benthic fluxes and to non-invasive measurement. A very quite new and a quite sophisticated method is the measurement of benthic oxygen uptake, non-intrusive, by eddy correlation. Eddy correlation was developed by Berg et al. In the early 2000s, and what you do is you deploy a small lander onto the seafloor, you have a velocimeter, and you measure with a fast, usually Clark type oxygen microelectrode, the change of the oxygen in concentration near the seafloor. And then the flux can, in a very simplified manner, calculated from the bottom motions and the bottom friction and the concentration, in theory. Practically, it is very difficult to calculate the fluxes from these measurements, and the data processing takes a lot of time and effort to create really realistic flux measurements. Because here in this benthic boundary layer, from the sediment-water interface up in the water column, there is a logarithmic increase in current velocities and also logarithmic increase in the turbulence diffusivity and also in oxygen. And one also needs to include the bottom, the seafloor roughness into the calculations. All these parameters go into the calculation, and it's quite complicated and time consuming. I never did it and I never will do. But the advantage of these methods is it's non-invasive and it integrates over a large surface area of the seafloor that contributes to the flux, and it considers both the diffusive and the advective transport across the sediment-water interface, and it's especially useful on sandy sediments. Another method to measure sediment water fluxes is a lander equipped with a microprofiler, and what I showed in the sediment core, you can also measure in situ on the seafloor the oxygen penetration or nitrate penetration, depending on the sensor, into the sediment using microoptodes. And if you combine it with a laser scanner, you can also investigate the topography and bed form migration, and then you can model oxygen flux dynamics in the field. And this is done by a PhD student at Max Planck Institute in Bremen, and I will also kind to provide his first results to present here. So I will quickly show how this looks on the seafloor. So the lander is deposited on the seafloor. This red stripe is the laser scanner who scans the seafloor, and this fork are the oxygen optodes that measure in situ the oxygen penetration depth.
For how long? Does it have to stay there?
This usually stays for about 5 to 10 hours. But it goes more slow in reality. So, and if you combine these the results from the microtopography from the laser scanner and the number of oxygen profiles, you can arrive at such a three-dimensional model result. This shows the upper sediment and sediment water interface, and this example shows a sediment surface with no bed forms and a very low surface current. And you see that at very low surface currents, the oxycline in the sediment is quite shallow, close to the sediment surface. At higher bottom currents and stationary bed forms, so ripples that don't move, you see that the penetration of oxygen goes deeper in the ripple troughs, as I showed before, and you see the oxycline is deeper, so bottom water is pushed into the sediment, especially in permeable sediments. So the oxycline and the redox regime in permeable sediment really depends on the bed forms and on the bottom currents. And if we take sediment with migrating bed forms due to strong currents, we really see a deepening of the oxycline into the sediments and an intrusion of oxic water at the loop side of the ripples, and at the lee side the oxycline gets shallower.
Sorry, wir haben Why is that bubble?
This one?
Yeah.
Ignore it. that is probably a result of the interpolation technique. So just, it's not there.
At the bottom of this oxycline, for example, the middle one,
Yeah?
how old do you expect the sediment to be?
How?
How old?
How old?
Yeah.
Oh, that is very difficult to say because permeable sediments with strong bottom currents, there is a constant reworking of sediments.
Okay. So you have new inputs of
Yes.
organic matter.
Yeah. Now I'm going to present invasive techniques to measure benthic fluxes or flux across sediment-water interface, and a technique that is around for about 30 years are benthic chamber landers. And the principle of benthic chamber landers is, like with the sediment core enclosure, you penetrate a chamber. It can be round shaped or rectangular shaped into the sediment. So it should be halfway in the sediment, about 15 to 20 centimeters, and a water column above. And you stir the water column. There are sensors inside the chamber that measure, for example, conductivity and oxygen, CO2, and then the chamber is equipped with siren samplers, and you can take samples out of the sediment overlaying water, as you do manually in the incubation experiments, in these syringes. Currently, there's about 20 different types of landers in different institutes, and they can be used for measuring benthic fluxes up to 11 kilometers depth. So Ronnie Glut from University of Odense, he had a few years ago an experiment in the Mariana Trench where he measured benthic fluxes with a lander at 11 kilometers of water depth. Well, the design looks then a bit different. That's the principal design of the lander we use in our institute. The lander is equipped with two round-shaped flux chambers. They are equipped with different sensors. Outside the chambers, the lander is equipped with a CTD. Then a deep sea battery provides the energy. We have also a current meter on the lander. The lander is equipped with weights to keep it steady on the bottom. And we have a pop-up buoy. So the deep sea landers are free falling. They are equipped with buoys and weights, and they are free falling. And when they are taken up or recovered from the sediment, acoustic signal is sent, and the weights are released, and the lander pops up. We do it differently. We release the lander on a wire to the sediment. Then the wire is released from the lander, and the lander sits as it is. And when we want to recover the lander with acoustic signal, we release this pop-up buoy from the bucket, and the pop-up buoy is connected to the lander with a rope. And then when we take up the buoy from the surface, we can winch the lander on the rope back to the ship. As you can imagine, this is sensitive to heavy sea. So if there are bad weather conditions, we do not deploy a lander because it's quite risky to lose one. And in June we had a cruise in the North Sea, and the weather conditions were not so good, but we had to get out the lander, and we lost one lander. But we could get it back a few days later. Yeah?
No, I'm just wondering, maybe you said that, but how big is it?
The enclosures.
No, the whole thing.
The whole thing. Oh, the deep sea landers, they are huge. They are 2.5 or 3 meters high, and at least 2 meters in diameter. This one is smaller. Is the total height is, up to here. It's about 1.70 meters, and the diameter is 1.5 or 1.8 meters. So we try to keep these landers compact and small, that to avoid topping over when we lower it to the seafloor.
Is there no other technique than using the weights that you deposit at the seafloor? It sounds a little bit environmental unfriendly to...
In the deep sea?
Yeah.
Up to now, not. But we don't leave it on the seafloor in shallow seas. We recover it with the weights. Yeah?
Maybe I missed it, but is there any way to calculate the rate of sedimentation? Do you use any instrument for that? Like see
the
how much
rate-
particles, just
You mean the height of the sediment in the water column, or?
how much particles just sink to the bottom? If there's a way to calculate that every hour.
Yeah, it is, but not on such short time scales, because sedimentation rates are usually, even in the coastal sea, up maximum a few centimeters per year. You can't. Well, you could deploy sediment traps, where you can, in the water column, collect the material that is settling. But a sedimentation rate in a time scale of a few hours, it's too short. Okay, we calculate the benthic fluxes in the flux chamber basically in a similar way like in incubation. So we took the samples with the sirens, we analyzed them, or we take the continuous measurements from the electrodes. And this example shows nitrate and ammonia concentration over the time of the incubation. Usually we deploy a lander ideally for a tidal cycle, so 25 hours or 24 hours. But if we know that the window of good weather is it's short, then we deploy it for a shorter period of time. And then we calculate it the same way. We plot a linear regression line over the change in concentration over time. We use the same formula. We use the height of the water column in the enclosure and the concentration change over time to calculate the fluxes from the sediment to the water or oxygen uptake. And in this example, we had about 0.66 millimole ammonia per square meter and day released from the sediment, and 0.11 millimole of nitrate. And this is an example from a sandy sediment in the North Sea in September last year. I'm introducing the lander we are using at our institute in a bit more detail. This is a newly developed instrument, so I had the opportunity to tailor or to develop an instrument together with another institute and a private company as I wanted to have it. It was a great luxury. And this is a lander especially designed for sandy sediments. Sandy sediments are quite compact, and it's difficult to penetrate a core into sandy sediments or in a chamber. And so we developed a lander that wiggles the chamber into the sediment. That's why the chambers are round shaped. It's two chambers. They're equipped with a stirrer disc to simulate the bottom, the flow and the friction. We can vary the speeds, and the chambers are equipped with oxygen optodes. We can directly measure CO2 with an optode, pH, and we have a conductivity sensor. And both chambers are equipped with sirens chambers. And outside the chamber we have a CTD with fluorescence and turbidity sensors, light sensor, oxygen optode, and we have also a Doppler current sensor. These white things around the chambers are to avoid, if the chamber's in the sediment and there's a strong current, it might wash the sediment away from the chamber, and so these white things avoid washing the sediment off. This is, as I said, this wiggling mechanism that the chamber is wiggled into the sediment. This technique was developed by Felix Janssen from Max Planck Institute in Bremen. And the lid of the chamber is equipped with a stirrer disc. And as I pointed out before, it's very important to in a good way simulate the hydrodynamic pressure, the hydrodynamic regime, in an enclosure to get reliable measurements, and we can adjust the stirrer speed to have either an advective regime in the chamber or a diffusive regime, depending on the sediments where we deploy the lander, either the permeable or non-permeable sediments. And you can see this is the hydrodynamic pressure within the chamber. So it differs from where you are in the chamber. So it's really important to simulate realistically the bottom currents. This is how it looks like, and the chamber is penetrated into the sediment. And I will show how this penetration takes place. So the land is deployed onto the seafloor. It's sitting there for some time. Here are nice ripples. Now it's wiggled into the sediment. The lid is closed and the measurements start. You can see how the currents move the sediment ripples. These are the first results from this lander. This is this shows the current speed and direction, and the red graph shows the current direction, and we can clearly see how the direction changes according to the changing tides. So we can really simulate, or we can really estimate the currents outside the chamber, and both chambers measure the uptake of oxygen over time and the pH, the decrease in pH in the chamber, and we can directly measure the release of CO2 due to the decomposition of organic matter. And then we can calculate back how much organic matter was decomposed. Now I would like to give you two examples of the application of benthic flux measurements. One is from the North Sea. Well, the North Sea is mainly influenced from the Atlantic, from North Atlantic through the Fair Isle current channel and to the discharges of the river Rhine, Maas, Elbe and Weser, and the anti-clockwise circulation driven by semi-diurnal tides and the wind. And as I mentioned in the beginning, there is the hypothesis that in the German Bight 10 to 30% of the total mineralization occurs in the sediment, depending on the water depths. So the shallower the water, the more remineralization occurs in the sediment, and we wanted to test it. And this is an example here from the German Bight with sandy sediments in May and in September, and the integrated pelagic respiration, so integrated over the whole water column. In the water column in May we found 84 millimole of oxygen per square meter per day, and the respiration in September 334. If we look at the sediment respiration, this is the red graph. In May and in September we have it about 15 to 16 millimole per square meter a day in both seasons. So this amounts in May 20% of the pelagic respiration of the pelagic respiration occurs in the sediment.
Can I ask, how do you measure the column respiration?
The water column respiration. We take water samples from a CTD and we measure oxygen by Winkler titration, and we take an aliquot sample and incubate them in the dark and measure it after, let's say, 24 hours. And with the different, usually oxygen is taken up, is consumed, and we calculate the oxygen consumption by the difference between the sample at the beginning and the end at different water depths. Usually we choose 3 to 4 depths, and then we integrate it over the whole water column. So we can see that in May 20% of the pelagic respiration occurs in the sediment, but only 5% in September. In the sediment, it's fairly constant. But in the water column, the respiration differs. So the share between water column and sediment is also seasonal dependent. Another example is also from the North Sea, from coarse-grained sediment with some epifauna. And here we try to develop a budget. So we had a daily production under sunlight condition of 220 millimole per square meter a day, 50% if the weather was overcast, and the daily pelagic respiration was 120. What we measured in the sediment with different methods, as this is ex situ and core incubation, different landers and in situ microprofiles, was about 10 to 25. Here, this high number is due to a benthic fauna in the chamber. So if there are bees in the chamber and start breathing, then the oxygen uptake goes up. So the pelagic respiration at that location in June this year amounted to 50 to 70% of the daily pelagic production, and the benthic oxygen uptake 10 to 20% of daily pelagic production. The next example is from the Black Sea, and here my headline is "Sediments contain the legacy of eutrophication." The Black Sea Western Shelf was during the 70s and 80s until the mid-90s heavily affected by eutrophication, overfishing, and climate variability. And this led to a collapse of both the pelagic and the benthic ecosystem. And we had large spread seasonal benthic hypoxia that completely wiped out the benthic ecosystem. And the large-scale occurrence of the seasonal hypoxia started in the 70s and increased of almost the whole northwestern shelf in the 1980s and the 1990s. In this graph shows a comparison of bottom water oxygen concentrations in the 1990s and in the 2000s, and we see that with the recovery from eutrophication in the 2000 years, bottom water concentration increased again. So how about the benthic nutrient fluxes? Another sign that eutrophication relaxed is when we look, for example, at the nitrate concentration in the surface water. Here you see the Danube River. And in the 1990s, in winter, extremely high concentration of nitrate in the surface water. If you compare it with winters between 2005 and 2010, a lot less nitrate in the surface water. Why did I choose winter instead of summer? Because in summer there would be more measurements. But in summer, phytoplankton takes up the nitrate, and the effect of anthropogenic nutrient input from the rivers is less prominent if you look at the picture from the summer. So I choose the graphs from the winter. If you now look at the sediment, this graph shows here the average oxygen uptake of the sediment in the 1990s, 2000. The ammonia flux from the sediment, nitrate flux, phosphate flux, and silica flux. We can see that between the 1990s and 2000s, the oxygen uptake from the sediment decreased significantly. If we look at the nutrient fluxes, only the phosphate flux from the sediment decreased significantly. All other changes are not statistically significant. So why did the phosphate flux decrease? It's simply because of higher oxygen concentrations in the bottom water. So the phosphate that is released from the sediment or due to decomposition is immediately caught by iron and by iron oxyhydroxides due to oxy conditions. despite the nutrient input from the water column decreased and primary production decreased in the water column, the release from the sediment did not decrease. So all the nutrients from eutrophication are still sitting in the sediment, and this leaching from the sediment goes on for several decades. So this is why I say sediments contain the legacy of eutrophication. So it takes long if the internal fueling of the system ceases long after external inputs of nutrients are reduced. And also, despite a decrease in eutrophication, it takes longer than the legislation period of politicians that we see an effect. And this is often, this is why often nutrient reduction policies are not very popular. They're expensive, but to see the effect, it takes a very long time. And if you don't see an effect, it's not very good for the politicians. So if they invoke a measure which is costly but doesn't bring immediate effect, they're not elected anymore. My next point is sedimentary archives. We can date the sediments using natural radionuclides and also artificial radionuclides from nuclear fission products. If you want to date the recent sediments, say for the last 100 years, the choice is lead-210. It has a half-life of about 22 years, and it's produced by the decay of natural uranium-238. We can date about 100 years due to the half-life. After about 100 years, this is 5 times the half-life, lead-210 disappears. So we cannot measure it anymore in the sediment, and that's why we can only date 100 years with lead-210. This graph shows an ideal sedimentary profile, for example, in a lake, which has a constant sedimentation rate. So the lead-210 is deposited with the particles on the sediment, and then it starts to decay. It decays exponentially. And this exponential decrease of concentration, when we know the half-life, provides us with a time information. We can use independent time markers like the fallout of cesium from nuclear bomb tests or from nuclear disasters like Chernobyl. The precursors of lead-210 and lead-210, cesium and also americium are gamma emitters, and we measure these with gamma spectrometry. So we take a sediment, put the sediment in a sample holder, close it gas tight, wait for a month, and then we can measure it. It's a long and tedious process, because usually it takes 1 to 2 days or to 1 week, depending on the activity, to measure one sample. And gamma spectrometers are expensive, and you can measure one sample in one spectrometer, and one spectrometer is about at least 80,000 euros. So dating a sediment core takes a long time, you know it. So to illustrate the pathways of lead and cesium into the sediment, so the degassing from the continents brings the precursors of lead-210 into the atmosphere, and then it decays to lead-210, and with precipitation, lead-210 is deposited on the sea or onto lakes. Also, lead-210 is produced in the sediment by radioactive decay. But what we want to measure is the lead-210 that settles with particles onto the seafloor, this lead-210 excess. And when we are measuring lead-210, we have to to divide these two sources. So we subtract the lead-210, which comes here from the water column, from the one in the sediment, based on the precursors. So we assume that lead-210 and the precursors are in radioactive equilibrium in the sediment, and that's why we measure the precursors, and then we can subtract one from the other, and we get the lead-210 that settled to the sediment. So I give now an example from a sediment core here in the Black Sea. That's the sediment core. In red is the lead-210 excess, the lead-210 which is of interest for us. This is the background lead-210 in the sediment. And in blue we see here cesium, and we see here americium. Americium is completely inert. It does not migrate in the sediment, given there's no bioturbation. So the place where you find americium, that is a sign that's the end of the atmospheric bomb tests in 1963. We have here the cesium peaks, and after 1963 also cesium should disappear in the deeper sediment. But due to bioturbation we see that it's also mixed down into the sediment, but we still have peaks. We have peak here and we have a peak here, and we attribute the peak to the to Chernobyl, but also to the end of the bomb tests. Then we can employ several models to calculate the sedimentation rate. The most often used models are two. One of them is a simple model, the one that which I showed here. And this is the called constant initial concentration. And the assumption of this model is, especially in a lake, you have a constant supply of lead-210 to the sediment and a constant sedimentation rate. And then you can easily calculate here from this exponential decrease the sedimentation rate. In other systems where usually the sedimentation rate varies with time, and then you can use another model, the constant rate of supply. It assumes the supply of lead-210 stays constant, but the sedimentation rate changes. And depending on how much you measure in the sediment, for example, if you have in a sample measure little lead-210, that means you have a high sedimentation rate because lead-210 is diluted. If you have high activity in a sediment, that means you have a little sedimentation rate because the signal is more strong. This is the basic assumption of this model. So for this sediment core, I use this constant rate of supply model, and this shows the age of the sediment based on lead-210. And this is the independent time marker from cesium of the end of the bomb test and the Chernobyl fallout, and this is the sedimentation rate. We can use this then to look how the particulate nutrient concentration in the sediment evolves over the depths of the sediment core. And I used particulate nutrients in the sediment and the sedimentation rate to calculate the boreal flux of nutrients in the sediments. Green is total phosphorus, red is total nitrogen, and total organic carbon in blue. The black line shows the discharge of suspended matter from the Danube River in million tons. And what we can see that earlier than about 1970, there are lower nutrient sedimentation rates than in recent years. So eutrophication started in the northwestern Black Sea in the early 1970s. And here we slowly start an increase of accumulation of nutrients in the sediments. This is another example to show how eutrophication is visible in the sediments for for a longer period of time. We see it still today, the higher amount of nutrients, the burial of nutrients in the sediments even long after eutrophication ceased. Now a quick excursion to my thoughts on the coupling of benthic and pelagic biogeochemical models. I'm not a modeler myself, and these are the thoughts which I think, or wishes that I have to modelers. I find it important that modelers and people who do the measurements and work with data closely collaborate. And it's important to evaluate the models with field data, but also to use the models to better understand the benthic processes. But also models are very useful to extrapolate, because you have seen that the measurements are quite an effort and time consuming, so you can just do a few measurements. But models can help to extrapolate the results to a larger area. I will base my my ideas on a paper that was written by Karl-Heinz Sothert and colleagues in about 15 years ago, and that is, to my knowledge, the best paper, the paper with the best overview about different ways of coupling benthic and pelagic models. So they looked at all models that were available, and they found a different extent of vertical or of resolution and detail in the models. So they said the most complex model is a model where the benthic compartment contains a dynamic, vertically resolved biogeochemical model of the sediment, which is coupled with a vertically resolved dynamic model of the water column. So this pelagic benthic coupled model considers particles sinking to the water column onto the sediment or incorporated into the sediment by burial and by eutrophication. And the model considers a solute exchange via molecular diffusion and advection near the sediment-water interface. It considers faunal irrigation and distinct layers of the sediment. You can imagine that such kind of model requires a high computational effort and time. A bit less complex model is a model which contains a dynamically vertically integrated model for the sediments coupled with a water column model. It still considers particles settling to the seafloor and exchange of dissolved substances. This is described as a function of the particle transformation rate. Even a simpler model is a model which considers the sediment as a reflective boundary. So the particles that arrive at the sediment surface are instantaneously transformed into nutrients and into CO2. It doesn't consider the processes that occur here in the sediment. And then there is a even simpler type of models where they consider either sediment-water exchange rate of bottom water or it considers the concentration of dissolved substances in the bottom water. This type is widely used, but it does not properly simulate the exchange processes. And the simplest type, it doesn't consider any sedimentary bottom. No particles arrive at the sediments. It's basically the material, the reactive material accumulates in the lowermost part of the water column. So how do these what kind of results do these models provide? These are the the model types, and here are the results. And in the plots is the solid line represents the most complex model, and then the dotted line is the lower one model simpler. And the graph shows the total nitrogen efflux from the sediment. In the vertically integrated model, the results are quite comparable to the most complex model, but you see already in the other models there is quite a discrepancy between the nitrogen efflux from the complex model with the other models. And you can easily imagine if you do not calculate the efflux of nutrients from the sediment, you get an effect, a negative effect on also in your pelagic model. So the input and output processes are not good represented if you have wrong or not good represented results from the benthic compartment. A good compromise between the computational effort and the output of results is the use of a sediment model that uses a vertically integrated sediment compartment and couple it to a water column biogeochemical model. So the computation is less expensive, and it has to integrate only the concentration of 2 fractions of sedimentary solids, and it is described prognostically. So it also offers the possibility to reproduce sediment response on short and long time scales, which these other 3 simpler types do not offer. So why should we couple benthic and pelagic models? So first of all, to understand biogeochemical processes, which has been done in this exemplary paper. Also to understand the role of ecosystem components for the assessment of ecosystem functioning. As I said, to extrapolate the point measurements to a larger area or to budget estimates, or for the assessment of ecosystem state drivers and forecast scenarios for decision making. Yeah, and that's it. Thank you for your attention and patience. And this is for the reading I recommend.